Hello everyone. In this video, we are going to perform a fast Fourier transform on the Artix-7 FPGA. We will be using the Xilinx FFT IP Core driven by a MicroBlaze softcore processor. This is part of a multi-part video series where I demonstrate two different approaches to running a fast Fourier transform. In the first approach, covered in the previous videos, we wrote a large Verilog file to manually calculate the fast Fourier transform of a given input vector. In this video, we'll take the second approach and use the IP core. So before we start, we must first explain how the fast Fourier transform IP block works. The Xilinx IP core is a simple piece of IP that allows us to perform a fast Fourier transform on a given vector. We use it by serially sending in our input vector through the S-axis data bus while holding the S-axis config bus set to the right constants. When we do this, the output will be serially generated through the M-axis data bus. Also, the A clock pin must be connected to the clock that drives the design, and the remaining outputs do not need to be used. When using the IP block, we must always set the S-axis config T data bus to a constant value by using the formula below. In this formula, n is the length of the fast Fourier transform that we want to do. Also note that the S-axis config T-valid input is always set to 1. We drive the bus signals in the manner shown below. Before moving on, we must first discuss the FIFO block. The FIFO block is used to temporarily store data as it moves between the processor and the FFT core. We can store a vector by serially sending data in and read a vector by serially sending data out. The data sent out always matches the exact order of the data sent in. For example, if we send in 5, 2, 10 into the FIFO, then when we stream data out, we get 5, 2, 10 streamed out. The FIFO block has 3 buses that allow data to move in or out. The first is S-axis, which is a bidirectional bus used by the processor to serially write data into the FIFO or read data out. The other 2 are one-way buses used by peripheral blocks. The ASIC STR RX bus is an input bus that receives data into the FIFO, and the ASIC STR TXD bus is an output bus that sends data out of the FIFO. To make this design, there are 6 total blocks that need to be added. They are the MicroBlaze processor, the clock generator, the FFT block, the FIFO block, the constant blocks, and the UART block. We must then set the settings for each accordingly. This is the complete block diagram of our design. As with any MicroBlaze-based system, it consists of 2 main sections. The first is the set of peripheral blocks specific to this design. These include the FFT, UART, FIFO, and constant blocks. The second is the set of core processor blocks, including the MicroBlaze, the clocking wizard, the processor system reset, the debug module, and local memory, which are all standard in every MicroBlaze design and are configured the same way each time. The ASIC interconnect serves as the bridge between the 2 sections, routing communication from the processor to each peripheral. This animation shows exactly how the code does the fast Fourier transform in hardware. First, the input vector is stored in local memory. Then, the processor writes the input vector into the FIFO through the bidirectional bus. Then, the FIFO sends out the input vector through its one-way bus into the FFT. Then, the FFT IP sends in the output vector through the one-way input bus on the FIFO. Then, the processor reads the stored output vector through the bidirectional bus and stores it in local memory. And finally, the processor then reads the output from local memory and sends it to be displayed on the UART line. Now that we've walked through the entire process, we're ready to start building it in Vivado. We start by creating a block diagram. We then add in the MicroBlaze processor, and then we add in the clock generator, and then we go into the settings of the clock generator to remove the unneeded ports. We then add in the UART block and the FIFO block. The settings for both of these can be left as default, because for this application, they are both fine. However, note that in a larger FFT project, if we wanted to increase the length of the FFT, we would need to change the FIFO settings to have more entries be stored inside to accommodate for a larger FFT. But since we are only doing an FFT that is of length 64 in this project, we can leave the FIFO in its default form. We then add in the FFT IP block. After that, we run block automation, and we set the processor memory to 64 kilobytes. Then after that, we run connection automation, and we regenerate the layout. After automating the connections, the fast Fourier transform block was not properly connected, so we move it into its correct location for now, and we'll deal with it later when the time comes. But before that, we need to go in and fix the way the reset was made. The reset needs to be made external, so we disconnect it and make it external. Then we also make the other pins in our constraint file external. Now we can start connecting the fast Fourier transform IP block to the rest of the diagram. To start, we must connect the clock input of the IP block to the main system clock. Then we make the other connections. After that, we add in the constants. And we also need to set the correct settings in the IP block. We have now finished the block diagram. Before moving on, let's just make sure that everything looks good. Everything looked good, so we can generate an HDL wrapper and then generate the bitstream. After the bitstream is generated, export the hardware. Make sure that you export the hardware into a known location. Then launch the Vitis IDE. When launching the Vitis IDE, make sure to have your project be made in a known location. When the Vitis IDE opens, click Create Application Project, then click Next, then select the exported hardware. You can find the exported hardware in the directory that you exported it to in Vivado. Then give your project a name and click Next. Then click Next on the screen after that. Then select the Hello World template and finish. Then go under the Sources tab and click on the Hello World code, and then paste in the code for this project. After that, click on the hammer to build your code. After the code is finished building, you should see a message that it was successfully built. After it has been built, click on Show View and search for the Vitis serial terminal. Then once you have the terminal up, open up the terminal on the same COM where your FPGA is connected. Make sure to use the baud rate and settings used by your UART block diagram from Vivado. Once you have set up the terminal, click the hammer to rebuild and then create a debugger. You just click Single Application Debug GDB and then click Debug. Then click on the Terminal tab and then click on the green arrow to run the debugger. You should see the results of the fast Fourier transform appear in the terminal. Then to run it normally, click the red square to end the debugger and click the normal run button. You can click the run button as many times as you want now. Also note that the results of the fast Fourier transform must be multiplied by the 8-bit value that we calculated with the formula. So in other words, each element shown in the terminal needs to be multiplied by 85. 85 is called the scaling factor. The reason for the scaling factor is because we chose to use radix 4 in our FFT settings. This is the ideal setting to choose because although it introduces this extra step, it makes overflow impossible. Also, it's important to remind you that the reset input was mapped to the first switch of the FPGA. That means that this switch needs to be set high in order for the design to work. The screen shown explains all of the code that we just ran in Vitis. Before ending this video, it's important to emphasize that these videos take a long amount of time to make. If you found this content useful and would like to see more, then consider buying a book or donating to my nonprofit organization. The link to my organization is in the video description. Also note that when you buy a book, you get access to 100% of the project files in the course and maintain lifetime access to any future materials that I release. Note that when you buy a book, you get access to the members-only Discord server, where you can ask me questions directly. The reason why it's important that I emphasize these things is because I would like to one day devote 100% of my time towards making these useful videos. But the only way that can ever become possible is if enough people buy books or donate. That's all for this video, and I'm looking forward to seeing you all in the next one.